Hi, I'm Miss Hearn. If you like this video, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos.
Before we actually work on the improper integrals, which is our goal for today, improper integrals do involve limits, and I just want to refresh your memory on some common types of limits that might come up as we're doing improper integrals. For example, here in example 1 for part A, the limit as x approaches 0 from the right of 2 minus x to the 4/3. So I wanted to remind you that when it says the limit as x approaches 0 from the right, so from the right means positive values, right? Looking at this function though, 2 minus x to the 4/3 power, the domain of this function is actually all real numbers. You can plug in any number you want to x to the 4/3. If that limit exists coming in from the right, it's the same as the overall limit. So you don't really have to worry about the from the right thing. We can just go ahead and find the limit as x approaches 0 of 2 minus x to the 4/3. And thanks to our limit laws, for this type of function, we can just plug in. So we just have 2 minus 0 to the 4/3, which is just 2. So it just most of the time can kind of ignore the to the right part. That's what I wanted to mention about that one. The next one, the limits involving natural log functions, you often want to refer to the graph of the natural log to help you with that. What's the limit as we approach 0 from the right on this one? Well, in this case, it's a little bit different because the domain of the natural log is only positive numbers. So referring to the graph coming in from the right towards 0. So I'm talking about going this way, right, towards the x value 0. What's happening to the function? It's going down towards negative infinity. And this is just using the graph to remind yourself of that. Another natural log limit that will come up frequently is the limit as x goes to positive infinity. Basically the right end behavior of the function. So what's happening to the y values as the x values get very large? Yep, it's increasing also. It's also getting very large. So we could just say equals positive infinity or just infinity. Just reminding you of these because they come up. Okay, how about the limit as x goes to infinity of the arctan pi over 2? That's right. So again, x going to infinity in both of these problems, you're thinking of the right end behavior of the graph. What is the y value doing at the end? In this case, the right end behavior we're going towards pi over 2. So what I do is I literally stop for a moment and think about the shape of the arctangent graph. So remember, the tangent graph looks like this, right? It has asymptotes at negative vertical asymptotes, negative pi over 2, pi over 2. When you switch all the x's and y's, you get this graph. And so, okay, so let's do our first survey of today. You're going to find the limit as x goes to negative infinity of the arctan. So I have the graph right there for you to use, but oftentimes you have to, visualize it yourself. All right, so you did very well. 85% of you picked A, which was the correct answer. Let's take a look at where that's coming from. So again, on the arctangent, think of the graph. Here's the graph of the arctangent in the upper right corner of the screen. And when we say limit as x approaches negative infinity, we're actually talking about the left end behavior of the graph. So the graph, when we go out towards negative infinity, is settling along this horizontal asymptote at negative pi over 2, which has the y value negative pi over 2. So that's the reason why that limit is negative pi over 2. So remember, as again, the problems we're going to be working will involve limits, and there are certain things that come up regularly. If the natural log or the arctan come up, think of the graph. All right, so there are two types of integrals that are known as improper integrals, and they're labeled improper, as in not proper, for two reasons. They can be labeled improper because one of their bounds is infinity, or they can be labeled improper because somewhere in the interval of the bounds, whether it's at the endpoints of the interval of bounds or somewhere in the middle of the interval of bounds, doesn't matter. Somewhere the function is undefined. There's a vertical asymptote. So as examples here, let's focus on this one on the left first. The integral from 0.5 to infinity of 1 over x. So the function 1 over x is defined everywhere on that interval because it's only undefined at 0. So that's not the problem. It's not the vertical asymptote. The problem is that the bound is infinite. So think about what this means. Remember, a definite integral represents the area under a curve between the curve and the x-axis on a given interval. So we're actually being asked to find the area between the function 1 over x and the x-axis on an infinitely long interval. You would think it would seem reasonable to think that if it's an infinitely long interval, that the area would have to be infinite, but it's not necessarily, because it depends on how fast the function approaches the x-axis. If it gets small enough, fast enough, then there's actually a bound on the size of the area. It's kind of like the concept, have you ever heard of the concept, how long does it take me to cross the room if I go half the remaining distance every time? And yeah, it takes infinitely long. But think about this. What that means is you can spend forever, but how far have you gone? There's a limit to how far you actually get to go, right? You never go farther than the wall. So in this case, the area is the thing with a limit. So you're walking forever, but the area never grows past a certain value. So it's weird, but it's true that you can have an infinitely long interval and the area is finite. Of course, a lot of times it's infinite too, and our job is going to be to determine whether it's infinite or not. And if it's not infinite, how big is the area? Oh, and by the way, we call that type 1 improper integral, is when we have an infinite bound. You might have 2 infinite bounds. It might go from negative infinity to positive infinity, or you might just have one of them infinite. Type 2 is the one I mentioned that you have a vertical asymptote. So here on the right, we have that kind. The integral from 0 to 3, notice no infinite bounds, of 1 over x. But the problem is that 0, that end point, that lower limit, the function is undefined there. In fact, 1 over x has a vertical asymptote at 0. As we get closer to 0, the graph gets closer and closer and closer and closer to 0. The y values are getting infinitely large. So this area is actually endless. It goes up forever. So again, it's just a vertically oriented, infinitely long piece of area. And again, the question is that area going to be finite or infinite? This is called a type 2 improper integral. And it's possible for it to be either finite or infinite. When the area is finite, what we say is that the improper integral converges to a particular value. When the area is infinite, we say that the improper integral diverges. So you need to know 4 new vocabulary words, well, really 5. You need to know what improper integral is. You need to know what type 1 and type 2 improper integrals are. You need to know what it means for an improper integral to converge, and you need to know what it means for it to diverge. In this first part of the lesson, we're just going to focus in on the type 1 improper integrals. Those are the ones that are easiest to spot because they have infinite bounds. So right away, you know you have a problem. The other ones are a little sneakier. You got to pay close attention for those. All right, so what we're going to do, for example, if we have an integral from some finite number to infinity, because here's the idea. Remember, we're looking at an area. We're looking at an area under a function and it goes from A out to forever. We can't just calculate to forever. So what we do is we pick some end to the interval B. We find the area between A and B, and then we let B get a little bit bigger. We move B outward and we find the area between A and that B. And we keep doing that. We let B get larger and larger and larger, looking at the area each time, and we see if it trends toward a finite value. But what is that I'm describing? That's taking a limit as B approaches infinity. So anytime you see an infinite bound, and it doesn't matter if that infinite bound is at the top or at the bottom or at both, we're going to rewrite the integral with definite bounds, with defined bounds A and B, and take the limit as they approach infinity as appropriate. So if we have a negative infinity, then it's going to be A that's approaching negative infinity. So we'll take the limit as A approaches negative infinity of the integral from A to whatever that value B is. Now, if it's in negative infinity to infinity, it's really the sum of two improper integrals. It's the sum of one that goes from negative infinity to some number C plus the one from C to infinity. So you'll actually have to deal with two limits in that case. So we're going to look at all of these cases. So let's start with the question, is the area between the x-axis and the function y equals e to the negative x on the interval from 0 to infinity finite or infinite? If it is finite, what is its value? Okay, so when we're talking about the area between a function and the x-axis, we're talking about a definite integral. In this case, an improper integral, but still, what you want to do is to say the area A is equal to the integral from what to what in this case? What's the interval that we're interested in? 0 to infinity, good. Of the function e to the negative x with respect to x. So that's the integral representing the area in question. Immediately rewrite it as a limit. So in this case, the infinite value is only at the top. And it doesn't really matter what variable, but we usually use B when it's the one at the top, and we use A when it's the one at the bottom, but it really doesn't matter. But in this case, we have the integral from 0 to B of e to the negative x dx, and we want to see what happens as we let B get larger and larger. So we're taking the limit as B goes to infinity of that definite integral. So what you're going to do is ignore the limit at first and just evaluate the definite integral using B as one of the bounds. So one of the bounds is a variable. So what is the integral of e to the negative x? That's right, negative e to the negative x. And we're evaluating that from 0 to B. Keep writing the limit, but ignore it for the time being. So now we're going to say the limit as B goes to infinity of, we're going to plug in the top bound and the bottom bound. So we're going to have negative e to the negative B minus negative e to the negative 0. So that's the limit as B goes to infinity of, let's see, it's going to be negative e to the negative B plus 1. Personally, I find it easier to think about the limits when I use positive exponents. So I'm going to write this as the limit as B goes to infinity of negative 1 over e to the B plus 1. All right, so what would that limit be? 1, that's right. The denominator e to the B is increasing without bound, and the numerator is staying fixed and constant. And when we have that, we know that the overall value of that term is going to 0. So we have 0 plus 1, which is 1. So it turns out that in the graph, remember what e to the x looks like, or sorry, e to the negative x. And it turns out that the area between 0 and infinity, all of this area that goes on forever, despite the fact that it has an infinite length, it has a finite area, and that area has a value of 1. Okay, any questions about that problem? Not too bad, right? All right, so let's do another survey. Why is the integral from 0 to infinity of e to the negative x dx considered an improper integral? All right, you did great. 81% of you said B, which is correct. So the reason why this particular integral is considered improper is because its upper limit of integration is infinite. This makes it a type 1 improper integral. That's how they'll refer to it. It is true that this integral is which? Convergent or divergent? Convergent, because it has a limit. And but it's not true that it's undefined at 0. Okay, but being convergent or divergent doesn't affect whether it's type 1 or type 2. All right, let's look at another example. Evaluate the given integrals. All right, so here we clearly have a type 1 improper integral because one of our bounds is infinite. What's the first thing that we do? That's right. We write it in the form of a limit. Limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Okay, what is the integral of 1 over x? That's right. Natural log of the absolute value of x. So we have the limit as b goes to infinity. Natural log absolute value of x evaluated from 1 to b. All right, so now we're going to just plug in our bounds, still writing the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. Since b is approaching infinity, we're only concerned about positive values, so I don't really have to write the absolute value thing. And what's the natural log of 1? 0. So this is really the limit as b goes to infinity of the natural log of b. Would you agree? Okay, and what did I tell you at the beginning of class? When you have limits involving the natural log function, you want to think about the end behavior of the graph. That's right. So we're going to remember that the natural log function looks like this. We're talking about the right end behavior. So what's happening to the y values there? It goes to infinity. It goes to infinity kind of slowly, kind of at a very slow incline, but it does keep going up, up, up. So this is going to just be infinity. This is actually a divergent integral or divergent improper integral. That means that the area between the natural log and the x-axis on the interval from 1 to infinity is infinite. Any questions about that one? Okay. The next one is the integral from 1 to infinity of 1 over x squared. It's interesting because you can have very similar improper integrals and have very different results. So let's take a look at this guy. Okay, let's see. We have infinite bound. So we're going to rewrite this improper integral, this type 1 improper integral, as a limit. Limit as b approaches infinity of the integral from 1 to b. And I'm going to write this as x to the negative 2 because I find it easier to integrate. X to the negative 2 dx. Right, so we're going to have the limit as b goes to infinity of negative x to the negative 1 evaluated from 1 to b. So we have the limit as b goes to infinity of this is going to be the opposite of b to the negative 1 minus the opposite of 1 to the negative 1. So we have the limit as b goes to infinity of negative 1 over b plus 1. So what happens to negative 1 over b as b approaches infinity? It goes to 0. That's right. So we have just 0 plus 1 equals 1 again. So what's the difference between these two improper integrals that we just looked at? The 1 over x and the 1 over x squared. So thinking of the graphs, this is the 0.11. They're both going to go through the 0.11, right? Oops, I think I'm going to read it on. So let's say this is 1 over x. How is 1 over x squared going to compare. So it's going to get steeper faster up here, and it's going to approach 0 faster down here. So the area got small fast enough that it didn't turn out to be infinite. Whereas with 1 over x, it didn't get small fast enough. So this one is convergent. And the only difference was that squaring the x. Excellent observation. 1 over x cubed should be convergent because it's going to get small even faster than 1 over x squared. It's going to have a smaller area. Very good. Let's take a look at this one. This one has 2 infinite bounds. The integral from negative infinity to infinity of 1 over x squared plus 1. So whenever you have 2 infinite bounds, you want to break it up into 2 type 1 improper integrals. It doesn't matter where you break it up usually. So for example, one person might break this up at 0, another person might break it up at 1. Doesn't really matter. What do I mean by break it up? So we could have the integral from negative infinity to 0 of 1 over x squared plus 1 dx plus the integral from 0 to infinity of 1 over x squared plus 1 dx. Together, those make the entire integral from negative infinity to infinity. So we have 2 type 1 improper integrals. This first one, we're going to have to think of as a to 0. So we're going to take the limit as x approaches, not x. The limit as a approaches, good, negative infinity of 1 over x squared plus 1 dx. Plus, how would I write the second one? Integral 0 to b, 1 over x squared plus 1 dx. The integral symbol needs work. Now, who remembers what the integral of 1 over x squared plus 1 is? Arctan, that's right. So this is going to be the limit as a approaches negative infinity of arctan of x evaluated from a to 0 plus the limit as b approaches infinity of the arctan of x from 0 to b. Now we're going to plug in our bounds. So we have the limit as a approaches negative infinity of arctan of 0 minus arctan of a plus the limit as b approaches infinity of arctan of b minus arctan of 0. Okay, so remember arctan of 0 means we're looking for the angle theta so that the tangent of theta equals 0. What angle has a tangent of 0? 0. So both these arctans of 0 are going to just be zeros. So we have the limit as a approaches negative infinity of negative arctan of a plus the limit as b approaches infinity of arctan of b. Now, what did I say at the beginning of class? When you have limits involving the arctan, you want to think about the graph, right? Are you visualizing the arctan graph in your mind? Can you see it? So it looks like, all right, so what's the limit as a approaches negative infinity of arctan? Negative pi over 2. So this is the opposite of negative pi over 2. Plus, what's the limit as b approaches infinity of arctan b? Positive pi over 2. That's right. So we're going to get pi over 2 plus pi over 2 is 2 pi over 2, which is just pi. So pi turns up in yet another strange location. It's the area under the curve 1 over x squared plus 1 forever. The whole thing, the whole curve from negative infinity to infinity adds up to pi. You never know where pi is going to pop up next. All right, now there's an example in the book that's real important. It's going to be our example 4 today, but it's example 3 in the book. It deals with improper integrals of a particular format. That's the format of the integral from 1 to infinity of dx over x to the p. we've actually already seen two of these. We did the integral from 1 to infinity of where p was the power 1, so just 1 over x. And we did where p was the power 2, so 1 over x squared. We've done two of these already. You made the excellent observation that, well, if 1 over x squared converges, so must 1 over x cubed, and so on. What this problem talks about is for what values of p, or for what powers, does the integral converge? And what would be the value of the integral? We're going to actually get a formula for the value of that convergent integral for any of those powers. First, we're going to just look at the integral from 1 to b, and then we're going to take its limit. So let's talk in general. If you have the integral from 1 to b of dx over x to the p, right, what would its value be? So I'm going to think of this as the integral from 1 to b of x to the negative p dx. It's easier to apply the power rule that way. And what do we do when we have x to a power? Add 1 and divide by it. Good. So we're going to have x to the negative p plus 1 divided by negative p plus 1. And we're going to evaluate this from 1 to b. All right. I actually prefer to think of it not as negative p plus 1, but as 1 minus p. But in any case, in the next step, we're going to plug in b to the x. Sometimes I accidentally plug these into the p and confuse myself, so be careful with that. So we have b to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. So now we're going to take the limit as b goes to infinity of this integral. So we want to take the limit as b goes to infinity of, and then we have b to the 1 minus p over 1 minus p minus 1 over 1 minus p. Now, for the purposes of this integral, p is a constant. P is not changing. So 1 minus p is also a constant. So that means that we can actually bring the 1 minus p out of the limit. So this is going to be 1 over 1 minus p times the limit as b goes to infinity of b to the 1 minus p minus 1. All right, now, again, when we're taking limits to infinity, it's easier to think about the variable that's approaching infinity being in the denominator, right? Because when the variable that's approaching infinity is in the denominator, then and the numerator's fixed, we get 0 for the limit. So we're going to think of this as 1 over 1 minus p times the limit as b goes to infinity of 1 over what? If you want to rewrite b to the 1 minus p as 1 over something, what do you have to do to the exponent? Take the opposite, that's right. So we're going to think of it as 1 over b to the p minus 1. Let's think about this for a minute. Under what circumstances is this thing going to go to 0? We want to know when this limit's going to converge. It's going to converge if that first term goes to 0, right? If that goes to 0. That goes to 0 if and only if the denominator is getting very, very large, right? So when would b to the p minus 1, when would that go to infinity? If that goes to infinity, that would mean that we have convergence. Well, it's only going to go to infinity when p minus 1 is greater than 0. Yes, when it's a positive. So we want p minus 1 to be greater than 0. In other words, when p is greater than 1, that limit is going to converge. Otherwise, what's going to happen if p minus 1 is less than 0 is it's going to flip back up into the numerator. It's going to become positive going to infinity. So that's the only time it's going to converge. When it's less than 1, it's going to diverge. Now, with this limit, we can't say what happens when it's equal to 1, because why? Because when it's equal to 1, we get undefined, right? Okay, but we can at least say that it converges when p is greater than 1, which is consistent with what we've seen before, because remember when we had 1 over x squared, that was p was 2, p was greater than 1. And not only that, but since this guy is going to go to 0 under that circumstance, that limit is actually going to just be. So when p is greater than 1, we not only know that the integral is going to converge, we also know what it converges to. -1 over 1 minus p. What's another way to write -1 over 1 minus p without the -1 in the top? That'd be the same as 1 over what? P minus 1. That's right. So when p is greater than 1, the integral will converge to 1 over p minus 1. And when p is less than 1, it's going to diverge. It's going to be infinity. Now, again, with this particular setup, we can't say what happens when p is equal to 1, but we don't need to because we actually already figured that out. What happened when p was equal to 1? Yeah, it turned out to be infinite. Remember, it turned out to be divergent. Up here, we already did that case. This is the case of the integral from 1 to infinity of 1 over x to the p dx when p equals 1. And it was divergent. So now we know everything there is to know about the convergence and divergence of this particular type of integral. What happens when p is equal to 1? So therefore, the integral converges to the value 1 over p minus 1 if p is greater than 1, and it diverges if p is less than 1. And what happens if p is equal to 1? It also diverges, yes. This limit that we just calculated is only for, doesn't work for p equal to 1, only for p greater than 1 or p less than. We had to look separately. Remember, we proved up here that the limit was infinity when p was equal to 1. So you're right, this work that I did right here would all be undefined if p were equal to 1, but we didn't use that for that very reason. We had to take a different approach because you actually end up using a natural log integral. Other questions? All right, so the nice thing about this is that gives us a whole class of improper integrals that we don't even need to integrate. We can just recognize that it fits the pattern and use the formula. We'll practice that in a minute, but first I want you to answer this question. For which values of p is the integral from 1 to infinity of 1 over x to the p divergent? I'm gonna make sure everybody's clear on this because this is so important. Not only is it going to be important for improper integrals, but when we start to do something called series, which we're going to be starting very soon, this is going to come up there as well. Very important. Okay, so a lot of confusion on this one. The correct answer is D. 36% of you got it right. If you got it right, give yourself a little pat on the back. All right, so let's see why the answer is D. D says that P is any positive or negative number less than or equal to 1. Then this thing is going to diverge. All right. So I think probably the easiest way to think about this is to think about some examples. However, before we do, I just want to point out that the answer is actually here, because this says that the integral will converge to the value 1 over p minus 1 anytime p is greater than 1. It's going to diverge if p is less than 1, and it's going to diverge if p is equal to 1. There is no mention of positive or negative, so therefore it could be either, right? P less than 1 could be anything. So let's take a look. So if p was on this number line, here's 1. If this is the value of p, anything from 1 and back is going to cause divergence. So let's look at specific integrals. We already said that when p equals 1, the integral from 1 to infinity of 1 over x to the first power, 1 over x dx, we knew that one diverges. Why would p equals 0 also be divergent? That's less than 1, so it must be divergent, but why? So let's see if we can think of a reasonable explanation. So we would have 1 over x to the 0 dx, which is the integral from 1 to infinity of 1 dx. Visualize the graph of the function y equals 1. From 1 to infinity, wouldn't that be an infinite amount of area? Because it's infinitely long and 1 unit high. It never shrinks. Remember, it has to shrink in order to stay small enough. So if you imagine the area from 1, well, here's y equals 1. The area from 1 to infinity, which goes on forever, is going to be infinite. It never shrinks small enough to keep it from being unbounded. Let's talk about less than 0, negative numbers. Why would the integral from 1 to infinity of 1 over x to the negative 1 dx, why would that be infinite? Because that's just the line y equals x, right? So what does y equals x look like? Looks like here's 1. So this area is growing as x, so it's definitely infinite. And if you do p equals -2, you're going to get x squared, and that goes up forever. So anything less, starting at 1 and going down, we have divergence. So the answer here was D, 1 or lower. Doesn't matter if it's positive or negative or 0. So to summarize, here's the convergence and divergence rule for the integral from 1 to infinity of 1 over x to the p dx. The integral from 1 to infinity of 1 over x to the p dx diverges when p is less than or equal to 1, converges to 1 over p minus 1 when p is greater than 1. This is a rule you're going to want to remember. So even though we've already looked at it, part A has the integral from 1 to infinity of 1 over x squared. Now that we know this rule, we don't have to do all the work. We recognize that it fits the pattern. In this case, p is equal to what? 2, which is greater than 1. So we know that the integral from 1 to infinity of 1 over x squared dx is going to be 1 over 2 minus 1, which is 1, which is the same value we got when we did the limit. And look, this is the one that you mentioned, 1 over x cubed. So in this case, p is equal to what? 3, which is greater than 1. So the integral from 1 to infinity of 1 over x cubed dx is going to equal what? 1 over 3 minus 1, which is a half. So it's actually half the size of 1 over x squared. Here's another one, part C, the integral from 1 to infinity of 1 over the square root of x. So what is p equal to in this case? 1/2. Good. So would you expect it to be larger or smaller than 1? Let's see what happens. The integral from 1 to infinity of 1 over x to the 1/2 dx equals 1 over 1/2 minus 1. Oh, shoot. Yeah, totally used the rule wrong. We were going to get a negative answer there, right? That doesn't make any sense. You can't have a negative area. This is less than 1, so it diverges. It gets very large, actually. Okay, any questions about any of those? It does not get small fast enough to keep from reaching infinity. All right, another bold. Which integral is convergent? Okay, more than half of you picked the right answer, which was C. Let's take a look. Okay, how do you approach this problem? Well, we know that p less than or equal to 1 diverges, and for p greater than 1, it converges. So you have to identify p. What's p equal to for A? -3. That's less than 1, so it diverges. What is p for part B? 1/3. Also less than or equal to 1 diverges. C is tricky. What is P? 5. That's right. You have to write it in the 1/over format, which changes the sign to a positive. So P is equal to 5, which is greater than 1, so it converges. So that's why C is correct, but let's just look at D. So to write D in the correct format is 1/x to the first. So P is 1, which is less than or equal to 1, which diverges. It kind of makes your eyes cross sometimes with the negative exponents and the positive exponents. So take your time, write it out. Has to be in the form 1/. All right, so that's the end of the lesson on type 1 improper integrals. And now we're going to move on to type 2. I do have, in addition to the homework questions from 8.7 related to type 1 integrals, I have a little worksheet that I created. So you need to do both. All right, so type 2 improper integrals. Again, 2 types. One has an infinite bound or 2 infinite bounds. The other one has to have a vertical asymptote somewhere in the interval. The example that I gave was the one with the 1/x in the interval from 0 to 3. The vertical asymptote was actually at the left end of the interval, but it could be anywhere in the interval. So how do we deal with this situation? Well, there are 3 basic cases, but it's not really that complicated. You either have the vertical asymptote at the left end, the right end, or in the middle of the interval. Those are the 3 possibilities. So if your vertical asymptote is at the left end, you're looking at the situation that we just saw up here, right? So if you we can't take the integral from 0 to 3 because the function is undefined at 0. So what we would do instead is we would take the limit of the integral from a to 3. We need our a to be approaching 0, but only from one side. From what side can a be approaching 0? If we're only interested in the interval from 0 to 3, there's only one direction you could be coming from towards 0. You have to be coming from the middle of the interval 0 to 3, right? So you're coming from the right. So if you're coming from the middle of the interval toward 0, then you're coming from the right. So you would say the limit as a approaches 0 from the right. This is always the case when it's the lower bound, it's going to be the limit coming from the right. If it's the lower bound, that's the variable, it's always coming from the right, would have to be, because the lower bound is the leftmost point in the interval. So that's a specific example of what they're trying to say in the textbook when you look at this definition. Improper integrals of type 2, the first case is where the vertical asymptote is on the left, where it's undefined at a. And so what they're saying is replace a with some variable. I use a because, well, anyway, and then come in from the right, take the limit from the right. So when you have a left endpoint undefined, you're going to take the limit from the right. Similarly, if it's the right endpoint undefined on the interval from a to b, then we're going to replace the upper limit of integration with a variable, and we have to come in from the left. So when you have a right endpoint undefined, limit from the left. It's also possible that the function is undefined right in the middle of that interval. So basically, you're going to do the same thing as when we had 2 infinite bounds. You have to consider splitting the interval up at the undefined value. which is going to create a union between two intervals, one which is undefined at the right end, so you need a limit from the left, the other is undefined at the left end, so you need a limit. It's the same every time though. So let's take a look. It can only be one of those three cases. Okay, so it says investigate the convergence of the integral from 0 to 1 of dx over the cubed root of x and the integral from -1 to 1 of dx over the cubed root of x. The simpler one is the one from 0 to 1. Let's start there. So we have the integral from 0 to 1 of, this is really 1 over x to the 1/3 power dx. Okay, so the first thing you have to do is to recognize that you even have an improper integral. These are trickier, they're subtle, and they can pop up, and if you don't pay attention, you might not ever even realize it and integrate incorrectly. There's no obvious infinite bound. So we're gonna have to start getting better. We've probably mentioned it throughout Calc 1 and Calc 2 that, you know, you got to make sure that your integrand is defined, but we always gave you integrals where the integrand was defined. So we never really paid much attention. Now we got to, because it's possible that it's not. So where is this integrand undefined? 0, that's right. So 1 over x 1/3 is undefined at 0 and only at 0. So in this case, we are considering the interval from 0 to 1. It's the left endpoint of the interval that where it's undefined. So we have to find the limit as x approaches 0 from the right. Yes. So we're going to write this as the limit. Oh, I said as x approaches 0, but that was incorrect. It's whatever variable we use for the lower bound, which usually is a. So it's the limit as a approaches 0 from the right, because 0 is the left endpoint. And I'm going to write this as x to the -1/3, so it's easier to integrate. Okay, so this is going to be equal to the limit as a approaches 0 from the right of, what is that integral? Good. 3x to the 2/3 over 2. Evaluated from a to 1. So we have the limit as a approaches 0 from the right of, that's going to be 3/2 minus 3a to the 2/3 over 2. Now, while the original function was undefined at 0, this antiderivative was not. 0 is in the domain. And we can plug in 0 for a, doesn't matter that it says from the right. So 3/2 minus 3 times 0 to 2/3 over 2. So that's just going to be 3/2. Okay, so that one is convergent. If you get a finite value, then it's convergent. All right, now let's investigate the convergence from -1 to 1 of dx over cubed root of x. So again, when we're looking at the interval from -1 to 1, we have to break it apart based on where the integrand is undefined. So we're actually going to have two integrals, the one from -1 to 0 and the one from 0 to 1, but we already did the one from 0 to 1, so that's nice. So I am going to write it out, but then we'll already know half of the problem. We'll have half the problem done. So we're going to have the integral from -1 to b, taking the limit as b approaches 0 from which direction? The left, because in the -1 to 0 interval, 0 is the right bound, and we have to come from the middle of the interval. So it's going to be from the left of, and I'm going to write this as x to the -1/3 dx, plus the limit as a approaches 0 from the right, the integral from a to 1 of x to the -1/3 dx. Okay, but this one we already know. This one turned out to be 3/2. Let's look at this one. So this is going to be the limit as b approaches 0 from the left of 3x to the 2/3 over 2, evaluated from -1 to b. That's going to be the limit as b approaches 0 from the left of 3b to the 2/3 over 2 minus 3 times -1 to the 2/3 over 2. That's going to be the limit as b approaches 0 from the left of 3b to the 2/3 over 2 minus 3/2. Okay, now what? First of all, do you agree with everything up to this point? Any questions so far? All right. Yes, so we're going to plug in 0. And we're going to have 0 minus 3 over 2 is -3 over 2. But that's just for this limit here, right? But the important thing is that as long as both of these limits converge, then so does the overall limit. In fact, the overall limit is going to be what? 0. Why would that happen? Thinking in terms of graphs, why would that happen? Very good. An odd function. It has symmetry across the origin. Convergent. Now, I don't want you to think, though, in a situation where we got -infinity plus infinity, would that be 0 and convergent? No. Okay, just to make sure. That's an indeterminate form, remember? Infinity minus infinity. Okay, so another tricky thing that can happen is just because something has an infinite bound doesn't mean it doesn't also have a vertical asymptote. So it's also possible for an improper integral to be both type 1 and type 2. What this means to you is, even if there's infinite bounds, you still have to check the integrand to make sure that it's defined everywhere in the integral. Here on out, we are always checking our integrands to see if they're undefined anywhere on the integral. All right, so let's take a look at this example. It says, consider the region that lies under the curve y equals 1 over x squared in the first quadrant. Is the area finite or infinite? Now we know from 1 to infinity that it's finite, right? If it was the integral from 1 to infinity, it would be finite. But now we're saying the entire first quadrant. So what interval are we looking at? 0 to infinity. So this is a different situation. Okay. So I'm just going to make a little note. We know the integral from 1 to infinity of 1 over x squared dx. Actually, not only do we know it's finite, what do we know that it's equal to? 1. Yes. But we don't know the integral from 0 to infinity of 1 over x squared dx. That rule that we talked about only works for integrals from 1 to infinity. Now it can inform you. Like, for example, I know that the integral from 0 to infinity is going to be bigger than 1, that's for sure. But it doesn't answer the question completely. So let's go ahead and talk about how we're going to deal with the integral from 0 to infinity 1 over x squared dx. The first thing we're going to do is check for vertical asymptotes. Check to see if it's undefined anywhere on this integral. So is it undefined? I shouldn't say it. Is 1 over x squared undefined on the interval 0 to infinity? Yes, at 0. That's right. Okay, so 0 is a problem. Now, just like when we had a negative infinity bound and an infinity bound, we wanted to split it up in the middle because we want to deal with the limits separately. We're going to do the same thing here. Where would probably be the best point between 0 and infinity to split up this integral? 1, because we already know about 1, right? Okay, so let's split 1 just because it's convenient. So we're going to consider the integral from 0 to 1 of 1 over x squared dx plus the integral from 1 to infinity of 1 over x squared dx, which we already know is equal to 1. So this first one, we have to use either a limit from the left or the right. We're going to write it as the integral from a to 1 of x to the negative 2 dx. This is the limit as a approaches 0, good, and from the right or the left? From the right, because 0 is the left endpoint, the lower bound. And then this one, we're just going to say plus 1 over 2 minus 1. Okay, so now we have equals the limit as a approaches 0 from the right of what? Negative 1 over x. Good. Add 1 to the exponent, divide by. We're going to get negative x to negative 1 or negative 1 over x from a to 1 plus 1. This is going to be the limit as a approaches 0 from the right of negative 1 plus 1 over a. Okay, so what happens to 1 over a as a goes to 0 from the right? Positive infinity, that's right. So we're going to have negative 1 plus infinity plus 1. Doesn't really matter the finite values. If you add infinity to it, you get infinity. All right, so this is divergent. The area is infinite. So while the graph of 1 over x squared has a finite value from 1 on, it has an infinite value between 0 and 1 because it keeps going up and it's not close enough to the y-axis. Okay, that's a good question. Let's go off to the side here, and whenever we're talking about something of the form of reciprocal of a number, just think of the reciprocal function. So let's consider y equals 1 over x. It looks like this. It's an x instead of an a, but that doesn't matter. What would be the limit as x approaches 0 from the right of 1 over x? This is our reference graph here. It goes upwards, right? We're talking about coming in from the right towards 0. So the y values are going to positive infinity. So always refer to this graph when you have a fixed value over a variable. Other questions? All right. Which integral is a type 1 integral, but not a type 2 integral? Okay. So the answer was B. 41% of you got it. Let's take a look at how we distinguish. Okay, so why is B the answer? Would anyone like to explain who got B, why you chose it? That's right. So when it says type 1, we have to look for only the one that immediately eliminates this one, right? Because there's no infinite bound. Type 1 means you have at least one, maybe two infinite bounds. So if there's no infinite bound, it's not type 1. Okay, but we want something that is a type 1, but not a type 2. So out of these three, what you have to do is figure out where are they undefined. When is x cubed minus 1 equal to 0? That can only happen in the real number system. That can only happen when x is equal to 1. Yes. So, but that happens to be a bound. So that means that this is a type 2. It's undefined at within the interval from 1 to infinity. For B, when is x squared plus 1 equal to 0? No solution, at least no real solution. So it's never going to be undefined on any interval. It could have been negative infinity all the way to infinity, and it would never be undefined. So this is not the type 2 because it's never undefined. And then for C, again, it is undefined at 0, right? X to the 5th. This is 1 over x to the 5th. So, and 0 is in the interval from negative infinity to 2. So this one is also a type 2. This is both. So A and C are both type 1 and type 2. But B is only type 1. Okay, let's look at this one. These last two examples of type 2 integrals are just some examples where you have to pay close attention to your integration techniques. Everything you've learned about integration techniques, you still need to apply even in these scenarios. So, for example, if we want to evaluate the integral from 0 to infinity of dx over the square root of x times x plus 1. First thing we have to deal with, yes, that's right, square root of, so check where it's undefined first. This is kind of a new thing that we're gonna have to deal with all the time, is to step 1, gonna check for undefined values. So in this case, it's pretty similar to a rational function. It's only going to be undefined where the denominator is 0, or, well, since there's a square root, negative numbers, but we don't have to worry about that. So we're going to have x could be 0 or x equals -1, but that's not even in the interval, it doesn't matter. So this is where we're concerned. So that means that we have a limit to set up for the lower bound and a limit to set up for the upper bound. So 2, we're going to write in terms of limits. Well, actually, let me say this. We're going to have to split it and write in terms of limits. Okay, now, again, in this particular case, it doesn't really matter where you split it. So I'm just going to go ahead and split it at 1. So it's the integral from 0 to 1 of dx over square root of x times x plus 1 plus the integral from 1 to infinity of dx over square root of x times x plus 1. Okay, now writing in terms of limits. How would I write the first integral in terms of limits? Very good. The limit as a approaches 0 from the right, because 0 is the left endpoint of the interval from 0 to 1. So it's going to be from limit as a approaches 0 from the right of a, the integral from a to 1, dx over square root of x times x plus 1. Plus, how are we going to write the second one as a limit? The limit as b approaches infinity, good. The integral from 1 to b, dx over square root of x, x plus 1, good. Okay, now there's a hint. Let u equal the square root of x and change the variables. Why don't you go ahead and get into your groups and work on this together and see what you can do with that. Use the hint there. Right, so we're changing the variables. It's not a regular substitution per se. So what we're going to do is, what did they say? Let u equal the square root of x. That means that what is x equals u squared, and what is dx du. So replace in the integral, you're going to replace the dx with 2u du. You're going to replace the x with u squared. And you're going to replace the square root of x with u. Also, we had in each case, we had a bound that was a bound that was 1, and a bound that was. So when x is a, that means that u is the square root of a. When x is 1, that means that u is 1. And when x is b, that means that it's the square root of b. So you can rewrite each of these using this. You with me? So if you didn't do that already, try that. All right, so for the first integral, when you make that substitution, you get the limit as a approaches 0 from the right, square root of a to 1, 2u du over u squared plus 1. When you make that substitution for this guy, you get limit as b goes to infinity, integral from 1 to square root of b, 2u du over u times u squared plus 1. In both cases, the u's cancel, leaving you with 2 du over u squared plus 1. Or you could move the 2 out front and think of it as 1 over u squared plus 1. But either way, the integral of 1 over u squared plus 1 is arctan of u in both cases. So we're going to have the limit as a goes to 0 from the right to arctan of u evaluated from square root of a to 1. And the limit as b goes to infinity of, 2 arctan of u, 1 to the square root of b. Okay, then you plug in your bounds. So you have limit as a goes to 0 from the right, 2 arctan of 1 minus 2 arctan of square root of a. And the other integral is 2 arctan square root of b minus 2 arctan of 1. Any questions up to that point? I think a lot of people, after I told you the u substitution to use, the change of variables to use, got to that point. And now let's make sure we can do the evaluation part. Okay, so arctan of 1 means the angle that you take the tangent of and get 1. So that's your pi over 4. And that pops up in both of them. And then let's talk about how we take the limit as a goes to 0 from the right of arctan of square root of a. Why is it that we're allowed to just plug in 0 there? Square root is a continuous function on its domain, which starts with 0. So we can plug in 0 to the square root, and then arctan is also continuous everywhere on its domain. So compositions of continuous functions we can just plug in. So we have 2 arctan of 0. Arctan of 0 is 0. So we just get pi, 2 times pi over 4 is pi over 2 minus 0 is just pi over 2 on the left. On the right, let's talk about the limit as b goes to infinity of arctan of square root of b. So notice that when b goes to infinity, the square root of b also goes to infinity. So this argument here is going to infinity. So we can refer again to the arctan graph. We're talking about the right end behavior of the arctan, so that's going to be pi over 2. So that's why I have 2 times pi over 2 here. So that's pi minus pi over 2 is pi over 2. So we got pi over 2 for each of the integrals, so they add up. Okay, so look at each step. Tell me, do you have any questions about any of them? So don't think of it as plugging in infinity. Think of it again as the end behavior of the graph of the arctan. So if this is the arctan graph and its argument going to infinity means we're looking at the right end behavior of the graph. So we're looking at x getting larger and larger and larger and larger. What's happening to y? It's getting closer and closer to pi over 2. Any other question? Okay, the last one of the improper integrals that I wanted to try to evaluate with you is example 4, the integral from 0 to 1, negative natural log of x dx. It says, why is the following integral improper? Determine if the integral converges or diverges. If it converges, find its value. So you tell me, why is it improper? It's okay that the natural log of 1 is 0. That's okay. The natural log of 0 is undefined. That's the problem. Yeah. So to answer this question, that's because the natural log of 0 is undefined. Remember what the natural log graph looks like? Vertical asymptote is 0. That's what's causing us a problem. All right, now let's try to figure out if this guy is going to converge or diverge. First, I am going to rewrite this with the limit. So this is going to be the limit of the integral from a to 1, where a is headed towards 0 from which direction? From the right. Good. Of negative natural log of x dx. Do we have an integral rule for the natural log of x? There is one, although not a lot of people have memorized it. There's an alternative if you haven't memorized it. No, we know that the integral of 1 over x dx is natural log, but that's not what I'm referring to. When we have the natural log in the integral, do we have a rule for that as well? Yeah, so integration by parts was the approach that we used when we had a natural log. Remember the Liotte thing? What does the L stand for? Logs. Now, why is it the number one thing? Because there's no rule for logs that we usually memorize. So what we're going to do is we're going to let u be the natural log of x. And we're going to let dv be the rest, which is just dx. I'm going to actually pull the negative out because it's just unnecessary. Just say negative natural log of x. So then du is going to be 1 over x dx, and v is going to be x. So we have the limit as a approaches 0 from the right of u times v minus integral of v du, evaluated from a to 1. Oh, opposite. So we're going to have the limit as a goes to 0 from the right of, let's go ahead and distribute that negative back in. So we're going to have the opposite of x natural log of x plus the integral of x 1 over x. Yeah. Okay, so that's going to be evaluated from a to 1. So that's going to be the limit as a approaches 0 from the right of negative x natural log of x plus, this is just the integral of 1, which is just x, evaluated from a to 1. So we have the limit as a goes to 0 from the right, and we're going to plug in our 1. We're going to have negative natural log of 1 plus 1, and then we're going to have minus negative a natural log of a plus a. Right, so we have the limit as a approaches 0 from the right of, this is just 0 plus 1, which is 1, and then we have plus a natural log of a plus a. Sorry, minus a. Now I can easily take the limit of 1 and the limit of a. But the limit as a goes to 0 from the right of a natural log of a is going to be a little more challenging. So I'm going to separate this. We have the limit as a goes to 0 from the right of 1 minus a plus the limit as a goes to 0 from the right of a natural log of a. So this first limit's just going to be 1, right? What happens with the second limit? Yes. What kind of indeterminate form is that?
Well, I think it's 0.
Yeah, 0 times infinity. So 0 times infinity indeterminate form. Do you remember what we did about that? You made it into a fraction, that's right. So we make this probably gonna pull the a down. So I have the limit as a approaches 0 from the right natural log of A over the reciprocal of A. Do you remember this? Why did we do that? L'Hopital's rule, that's right. Now we have a what? Infinity over infinity indeterminate form. So we can use L'Hopital's rule. So see how all of these things still happen, even when we're doing improper integrals. So according to L'Hopital's rule, this is going to be 1 plus the limit as A approaches 0 from the right of -1 over A squared, right? So that's going to be 1 plus the limit as A approaches 0 from the right of -A. So that's going to be 1 plus 0, which is, well, the tough ones. We had to use integration by parts, and we had to use indeterminate forms, change it to infinity over infinity to use L'Hopital's rule. Got everything. It's like a superstar of improper integrals. Okay, so as you can imagine, there are many cases where the improper integrals, we just can't evaluate them. Okay, the integrand is just too difficult. However, what we can do is use certain techniques to at least determine if it converges or diverges. And then if it diverges, we're done. There's no point in looking at it anymore. If we prove though that it is going to converge, we can then estimate at least using numerical methods. So, but I'm not concerned in this class with the estimating using numerical methods. I just want to show you 2 different tests that we can use to determine if an integral is going, if an improper integral is going to converge or diverge.
And that's what we're going to do in the next video. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Earn Mathematics, for more math videos.